Everybody, let us look into a numerical example for Grover search algorithm. The problem statement is we are given an unsorted database containing n equal to capital N equal to 1024 entries represented by a 10 qubit quantum register. Among these entries, exactly one element is marked and its index is 693. The task is to apply Grover search algorithm to locate this unique marked element, determine the optimal number of Grover iterations, calculate the evolution of amplitudes and probabilities, and show numerically how the algorithm boosts the success probability of measuring the marked element. Let us look into the solution for this problem. The unsorted list size is given to be capital N equal to 1024. Exactly one marked item is there, x stars, which is equal to 693, and its binary representation is also given. In the Grover's algorithm, the first step is to initialize the quantum register with all zeros and then apply the Hadamard gates for every qubit. This is done to put the quantum state into equal superposition. So we will get ket s, and this state which is equal superposition is given by 1 over under root of 1024 sigma x going from 0 to 1023 ket x. Now each basis amplitude is 1 over under root capital N, and it is given by 1 over 32 0.03125. Next stage for the Grover's algorithm after the equal superposition is to apply the oracle. Now oracle O will flip the phase of the marked element. So this equation gives us that oracle is acting on the quantum state ket x is given by -1. When x is equal to x star, then this will be, the power will be equal to 1, and this -1 will mark the x is equal to x star state. So this will only mark and this function will be equal to 1 only for the marked state. The next step in the Grover's algorithm is to apply the diffusion operator d, which is given by twice of the outer product of s minus I. This is basically doing the inversion about the mean. And then one iteration of the oracle and the diffusion operator forms basically one Grover iteration. So depending on the situation, there can be more number of Grover iterations also, so that ultimately we achieve the target state. Now let us try to form a sort of orthonormal basis, and we consider a two-dimensional reduction, and exact formulas for that are given like this. So ket w is equal to our target state. So this is the horizontal axis, and this is the vertical axis given by all other states except the target state. So ket w is the target state, ket w perpendicular is all other states except the target state. And this ket s is given by sine theta ket w plus cos theta ket w perpendicular. And we have already derived in one of my videos on Grover search algorithm that this sine theta is equal to 1 over under root n, and this is equal to 1 over 32, and we can find out theta from here, which is the sine inverse of 1 over theta to 1 over 32, and it will come out to be 0.031250. Now each Grover step is a rotation by 2 theta in the span. So in this, if you look at this, if you write a program and try to plot the overall problem, then you will see that the two axes are, one is ket w and one is ket w perpendicular. So therefore the red marked arrow gives me the x-axis, which represents the ket w axis, and this blue one, which is the ket w perpendicular, this represents the y-axis. So these two orthonormal bases or the axis span the complete plane. Right, so that's what is the meaning of each Grover step is a rotation by 2 theta in the span cat w perpendicular, and this is given by sine 2 raised to the power 2 into n plus 1 theta for cat w and cos 2n plus theta cat w perpendicular. This is because after every iteration there is a rotation, or there is a rotation towards the target state by an angle of 2 theta, right? So if you try some trigonometric manipulations, you will be able to find this cat w for after n iterations. This will be equal to this formula, and from here the amplitude of the marked state is we can calculate an amplitude of the unmarked state, which is basically all the states except the w state, the target state, and from here we can find out the probability, which is basically the amplitude square. So this is our marked state. The amplitude is given by sine of 2n plus 1 theta. If we take the square of this will give me the success probability for achieving the target state. And we also know that the optimal number of iterations are given by pi by 4 theta minus half. This we have already derived in the video that I was talking, that was developed for the Grover search algorithm. So if we put up the if we put all the values here, then this capital N, this small n is actually the number of iterations, and capital N is the number of items. This will come out to be one angle. We are checking it for 25 iterations. So therefore 2 iterations we are looking for. One is 25 and one is 24. So if we try to find out the success probabilities here, we will see that the success probability for the 24 iterations is more than the success probability for the 24 iterations. So therefore we will go for the 25 iterations for this particular problem. And we can perform the normalization check also, where the normalized state will be equal to 1. That shows the values are quite correct. Now we can also perform the geometric visualization. If you write the program for this and you try to simulate, you will be able to see the geometric visualization. The horizontal red axis represents the marked state direction w. So this is the state cat w. This is state cat w perpendicular. The gray arrows show the state vector after successive iterations. So the gray arrow, it shows that the gray arrow is moving towards the target state. After every iteration, it is moving by an angle 2 theta. So ultimately, after 25 iterations, it will reach to the target state with a very high amount of probability, success probability. So the picture shows how each Grover iteration rotates the state vector by 2 theta towards the marked state and amplifying its probability. Because diffusion operator will basically perform the amplitude amplification, and the basic principle of working of the diffusion operator, we know that it is inversion about the mean. So therefore it will basically enhance the probability of the target state and will suppress the probability, the likelihood of other states which are less likely. So this is the solution of this problem, and if we understand the Grover's algorithm, we'll be able to solve any problem related to this kind of data. Thank you.